Hello everyone. Thanks the organizer to give me this opportunity to present our recent work, Device-Independent Randomness Expansion Against Quantum Adversary. My name is Wen-Zhao. I come from the USTC, University of Science and Technology of China. This is a joint work with Professor Roger Colbeck, who provides theoretical support. I and my colleagues in the USTC are mainly responsible for the experimental part. You can find more details on our archive paper. First, let me briefly introduce the random number. What is random number? It can be roughly defined from two aspects. First, random numbers need to obey uniform distribution. As shown in the left table, needs to provide a well standard, which is the necessary test for random numbers to pass. Second, it should be unpredictable, which means that it should be independent of anything else. It should be independent of anything else. If we describe this mathematically, it can be written as the conditional probability distribution of xj versus E should be the same as its own probability distribution, which means the adversary E cannot affect the distribution of the output of random number generator. Random number has many applications. For example, we can use it for numerical simulation, which are very important in many industries in our modern lives, such as for weather forecast, and also in lottery, artificial intelligence, and information security. Random number plays an important role. Since it is important, we have motivations to do some research. The first thing that comes to mind is to build a well or standard random number generator for common random processes in our lives, such as tossing a coin or dice. They are essentially classical physical processes. Also, its output could have the perfect uniformity. In particular, the code for pseudo-random generator on the computer. They are predictable in principle. For example, if we could learn all the physical processes and related objectives in the process of tossing coins and know the seeds and algorithms of the pseudo-random generator, we could perfectly predict their outputs. However, in the case of quantum, it is unpredictable in principle. Considering a simple model in which a diagonal polarized photon incident on a polarizing beam splitter, then its probability of passing through and reflection is the same 50% in principle. This is guaranteed by the intrinsic randomness of quantum mechanics. Now, some commercial quantum random number generation could be found online. Let's consider the schemes to realize randomness generation. To simplify the model, we just consider to use a beam splitter to generate a uniform string, and then we estimate the amount of randomness, which should be unpredictable to adversary. Finally, we extract the uniform random bits by classical processing. However, for real devices, it is difficult to find a complete physical model that could describe all of the physical processes in a random number generator. Besides, how much quantum certified bits could be extracted from the raw string is also not an easy thing to calculate. Another motivation is to check a candidate random number generator working correctly. But up to now, we could not find any good test that only acts on the output. Based on these ideas, we find the device-independent protocol is a good way to realize a real random number generator. The figure is a conceptual sketch of the device-independent protocol. X, Y are two random strings. They input into two black boxes, Alice and Bob, and get output A and B, respectively. We do not pay any attention to the working status in the black box, but only consider the joint probability of the input and output P, A, B versus X, Y. In the premise of Alice and Bob have no communications between each other before producing their outputs, as long as the joint probability is proved to violate the Bell inequality. The output must contain unpredictable randomness. This protocol can be used to check a candidate random number generator and also easy to check. Not focusing on the specific devices makes it general and against different attacks, but difficult to experimentally achieve. Based on the device-independent protocol, the quantum randomness generation has a lot of development. Here I list the experimentally implementations of DI quantum random number generation. They all produce certified quantum random bits, but it can be found that in all demonstrations, the amount of output is much smaller than the input. Considering the need for the large amount of randomness in practical applications, DI random number generation is not enough. The net gain of randomness is necessary for promoting the widespread use of the device-independent random numbers. Therefore, we hope to realize device-independent randomness expansion, where the generated randomness surpasses the consumed. For the DI randomness generation, the randomness consumption is always 2 bits per round, and the randomness generated could never more than 2 due to the correlations between A and B. In order to achieve expansion, we need to reduce the entropy of consumption. One way is to use biased random bits. As shown in the figure, it is a schematic diagram to realize randomness expansion. We adopt the spot checking protocol to realize the net gain. For each round I, we could do the following processes. First, we set Ti satisfied a binomial distribution gamma and y minus gamma, 1 minus gamma, which is the output of the third random number generator. If Ti equals 0, the input of Alice and Bob, Xi and Yi are both 0. If Ti equals 1, each unbiased random number generator will be triggered and produce random number uniformly. We could obtain the stage assist value according to the joint distribution of input and output in the test rounds. During the implement of protocol, there is a condition related to the accumulate CHSH value to decide whether to abort. If the protocol succeeds without stop, we estimate the amount of randomness and perform extraction to get the final uniform random bits. Although the device-independent protocol does not require any knowledge of the devices, some necessary assumptions are also needed for randomness expansion. The first one is the implement of the protocol should take place in a secret lab. It is easy to think that we need to prevent the communications between devices and adversary to prevent the leakage of results. And also, as mentioned before, the communications between Alice and Bob before producing their outputs should also be forbidden. In fact, we can make them to be space-like separated or take while shielding to solve this problem. In addition to the 2 points above, Alice and Bob should also do not learn whether a particular round is test round or not. Otherwise, the CHS value in the test round cannot guarantee the protocol's security. To avoid this, the only way is to shield devices. The second assumption is the requirement for a trusted classical computer to perform randomness extraction. The third one is the requirement for the trusted random seed, both used in the basis choices of testing CHSH inequality and the seed for the extractor. The last one is that the quantum theory is correct and complete to limit all physical processes. With these assumptions, we achieve randomness expansion with entangled photons. This is our experimental setup. The system is located in a single lab. A is the entanglement source. The palm pulse with 718 nanometer wavelengths at 2 MHz repetition rate is injected into the PBKTP in the second loop. Pairs of entangled photons are generated via spontaneous parametric down conversion and are delivered to two sites through spatial optical paths. B represents the measurement sets Alice and Bob. Each of them uses a pixel to project the single photon into one of two predetermined measurement bases, and then detects single photons with a superconducting nanowire single photon detector as an SPD. In each round, a biased quantum random number generator creates a random bit Ti with a probability distribution gamma and 1 minus gamma to determine in advance whether this round will be a test or generation round. In test rounds, Alice and Bob each receive a random bit 0 or 1 from a local quantum random number generator to set pixel to 0 and halfway voltage accordingly. In our experiment, we do not close the locality loophole. In order to satisfy the non-signaling condition, we use shielding assumptions to prevent the communications between Alice and Bob, biased quantum random number generator, and the measurement size. The Haredi efficiency is about 84% and the fidelity is more than 99%. In order to maximally violate the Bell inequality, we create a non-maximal entangled state. We also realized randomness expansion in a separate work, in which the locality loophole was also closed in the test rounds. The setup used the same platform but differs in the location of Alice and Bob, while instead at two remote sites. The efficiencies are slightly reduced to be about 81%. As a comparison, we analyzed its performance using the EAT framework with the same error parameters as before. We experimentally carried out the DI randomness expansion protocol step by step. First, before the start of the main experiment, we implement a systematic experimentally calibration to predetermine parameters. From the pre-experiment test, we could obtain its CHSH value, omega exp. According to the EAT theory, we can get the least number of rounds n exp to witness expansion and the corresponding optimal bias gamma OPT. We proved the value of bias gamma is basically independent with error parameters. It is only related to the CHSH value. Second, according to the expected bias gamma, we design the biased random number generator and choose the actual number of rounds slightly larger than NEXP to guarantee the success of the protocol. We also choose different values of error parameters, including soundness error and completeness error. The soundness error bounds the distance between the output of protocol and perfect uniform random bits. The completeness error is used to define the failure probability to implement the protocol. Considering the statistical fluctuation during the experiment, we need to use the worst case to estimate the amount of randomness obtained. Delta represents the deviation of the CHSH value, which means that omega exp minus delta is the worst CHSH value considered in the estimation. Since there is a deviation between the actual gamma and the optical value, and the optical value is also related to the number of rounds, we studied the connection between the value of gamma and the expansion results. Although the actual gamma is slightly suboptimally, it is sufficient for expansion. Third, we estimate the amount of certified bits contained in the raw output and then perform the extraction. The results are different with varying completeness and soundness error. How to estimate the amount of randomness from the output is a quite difficult problem. We want a theory to cover most general possible attacks, and considering a practical scenario, it should be robust to finite statistics. In our experiment, we use the entropy accumulation theorem. By using the smooth mean entropy to estimate the amount of randomness, the EAT method provides relatively tight bounds on the amount of randomness that can be extracted against quantum adversary. Professor Colbeck developed a revised EAT theory to give a better result. For the randomness input, which is also the randomness consumed in the experiment, it could be divided into several parts to be calculated. One is the randomness consumption of biased quantum random number generator. Another is the input randomness in the test runs used for CHS tests. The randomness extraction also needs input random seed, but here we don't consider its consumption because it only plays a catalytic role. I will explain this in the next slide. Let me introduce the randomness extraction first. As shown in the bottom figure, the raw output of a weakly random string AB together with the uniformly distributed seed R is processed by an extractor with a deterministic algorithm. The extract bits M is a uniform sequence of randomness. Considering the error introduced in extraction, we use epsilon ext to describe the error of extractor. Epsilon h represents the smoothness parameters of the mean entropy. Then the soundness error of the extracted bits can be described with this formula. In our experiment, we used a quantum-proof strong extractor, Topliss matrix T. M is the length of extracted bits, N is the length of the raw output string. The matrix is completely determined by the elements in the first row and the first column, a total of n plus m minus 1 elements. For strong extractors, the initial seed is independent of the output. The seed of a strong extractor can be reused at the cost of the security parameter increased by epsilon ext. So we didn't take this part of the consumption into consideration. Our extract bits of our experiments are now available online. Now let's come to the results. There are two figures on this slide. The figure A is the minimum number of rounds to witness randomness expansion. To better show the progress in our experiment, we made it a comparison with our previous DI quantum random number generation work, which is the open square in figure A. It would take at least 118,000 hours to witness expansion with our revised EAT method at 200 kHz repetition rate, which is too long in practice. The circle and the cross represent the minimum number of rounds to witness expansion with our main and spacelike setup. In our experiment, we achieved the expansion protocol in 220 hours for the experiment with spacelike separation and 19.2 hours for our main experiment. The figure B is the randomness expansion rate versus number of rounds. Our results are represented by the cross and the circle. The asymptotic rates are only decided by the CHS value. We made a comparison between our two experiments. The left table is the counts of experimental rounds. The right table lists the detailed parameters used and the results obtained. The amount of output data in the two experiments are different. For our main experiment, we used a personal computer to perform the Topliss multiplication, which takes about 80 hours. For the experiment with the spacelike separation, we performed the extraction on a supercomputer, which takes about 250 hours. During our experiment, The randomness generation and the consumption with time are shown on the left figure. The changes of CHSH violation with time are shown on the right figure. We choose the average value of CHSH violation for each 24 minutes data at the point to observe its performance. In the experiment with space-like separation, we need to recalculate the system a few times according to the observed CHSH value. The green dashed lines divide the experiment into a few segments. In between, a recalculation was performed. With the same space-like setup, our group realized another randomness expansion experiment with the quantum probability estimation framework. It could against the quantum style information. The experiment started with a 3-hour training test, and a total of 12.5 hours data was collected. The theory was developed by the NIST group, and we also noticed their related works on the archive. They achieved the randomness expansion with the probability estimation. The total experiment time is 91 hours. You can see the talk by Ian Bao to find more details. Let me make a brief summary. We achieved the randomness expansion with the revised EAT theory and complete the experiments independently with 2 different experimental platforms. For the future, on the experiment, we plan to continue to improve the performance of our system, and we can also do some practical shielding methods to make the experiment more convincing. On the theory, the EAT method could be further improved to get more randomness, and we also consider to make a detailed comparison between the EAT and the QPE. That's all. Thank you for your attention.